Good.
Okay, so Sam Schonfeld from AFRL/Boston College will be talking about F10 and using EVE to correct F10.
Yep. Thank you. Can you all hear me all right and see the screen?
Yep.
Perfect. All right. Yeah. So this was originally work that was part of my dissertation, but has been recently updated, and I'll talk about that at the end with the collaborators listed here on the screen. So this was using EVE MEGS-A spectra to correct F10.7, particularly for use in ionosphere, thermosphere, terrestrial atmosphere models. So Kent mentioned F10 briefly and talked about all of these other metrics of solar activity and input to the atmosphere, but F10.7 is really the original input for these atmospheric models. So this is the 10.7 centimeter, 2.8 gigahertz radio flux, and being the original, I think it's still also the most used proxy for solar EUV in ionosphere thermosphere models. It's been observed for over 70 years. It's observed from the ground with very stable instrumentation that is well calibrated day to day, and being a ground instrument, it is cheap compared to flying stuff in space. And you can see why it might be used for these long times. So F10 is in the middle, sunspot number on the top, Lyman alpha flux on the bottom. You see they all correlate very well over solar cycle timescales. But it's not perfect. And sort of these issues are motivations for why other proxies have been developed. So F10.7 is not linear with solar activity. So during high activity periods, here we're looking at Lyman alpha flux and helium 10830 as a function of F10.7. And you can see that they're both nice and linear at low activities, but then they plateau, they sort of saturate once you get to higher activity levels. Also, looking at F10 versus sunspot number over many solar cycles, the red is solar cycles prior to 23, and the blue is cycle 23. So you see that there was some deviation between the F10.7 and the sunspot number during solar cycle 23. So all of this is to say that, F10, there are some issues with the F10.7 index, and the reason for those are that there's these different mechanisms that produce F10.7 on the sun. So first is bremsstrahlung. This is the free electron-ion collisional interaction, and it's depends on the plasma density squared in the corona, and because of that, it's produced in and around active regions and plage. There's also a optically thick bremsstrahlung component produced everywhere in the chromosphere, but this is typically relatively constant in time and is often considered a constant background. The other mechanism that produces F10.7 in the corona is gyroresonance. This is electrons spiraling in magnetic fields, and because it is this magnetic field activated emission, it occurs in the cores of active regions where we have the strongest fields. So the issue with these mechanisms and using F10.7 as an EUV proxy is that the bremsstrahlung component of F10.7, this collisional emission process, correlates very well with extreme ultraviolet because EUV lines are generated through collisional excitation. The gyroresonance component, there's no magnetically activated EUV emission. So the gyroresonance component of F10.7 does not correlate in amplitude. It does with time, but not in amplitude with EUV emission. So if you want to use F10.7 as an EUV proxy, as an input to atmospheric models, you really only care about the bremsstrahlung component. So what we're trying to do with this work is separate out these different emission mechanisms. And to do that, we use the EVE MEGS-A irradiance spectra. Here's a sample of one of those subsection of one of those spectra shown here on the left. Identify a number of relatively isolated and well-characterized iron emission lines, and use those to generate differential emission measures. That's just amount of plasma as a function of temperature over the whole sun. And here I'm showing you the DEMs on 3 days, but we have 4 years of EVE MEGS-A data. So here are the DEMs over 4 years. And from these DEMs, we can compute the bremsstrahlung component of F10.7. And that is shown here in the red. Compare that with the observed F10.7, which is the black. The green is the chromospheric component, which we've parameterized using the magnesium 2 quarter wing index. And then black minus red minus green gives us blue. This is the gyroresonance component of F10.7 over these 4 years. And so you can see that of the coronal contribution, which is the bremsstrahlung and the gyroresonance, the bremsstrahlung contributes more of F10.7 most of the time. There are individual rotations where the gyroresonance dominates, and that's due to 1 or 2 large active regions producing gyroresonance emission on the sun. But the variability between, say, multiple rotations is similar in scale with the gyroresonance and the bremsstrahlung. The issue is that the bremsstrahlung just has sort of a floor of emission, so it's contributing more. Okay, so identifying these components, we wanted to figure out, is there a way that we can pull out the bremsstrahlung component of F10.7 easily and use that as an index of solar activity, having removed the gyroresonance component. And so here I'm showing the bremsstrahlung in F10.7 as a function of F10. And you see we've got this nice trend, which is linear at low activity levels, as previous work suggests, and sort of falls off, plateaus at higher activity levels, again consistent with the relationship with coronal emission lines. So we can fit this distribution with a linear at low activity, power law at higher activity, and then get error bars on that fit, which you see the scatter in this distribution can be quite large in the higher activity, and we'll come back to that at the end. And then using this fit, we can compare this fit. So if we have a measurement of F10.7 of 150 on a given day, well, this fit says there should be something like 45 SFUs a bremsstrahlung emission, so we can use that fit and compare how that relates to the EUV. And so that's what we're showing here. The gray is EUV spectra over the whole MEGS-A range. The black here is the correlation, as a function of wavelength between F10.7 and the EUV spectra. The red is the correlation with this bremsstrahlung fit component. Blue is the magnesium 2 quarter wing index, and the green is based on photospheric magnetic field proxy. And you can see that pulling out the gyroresonance component, just considering the bremsstrahlung fit to F10.7, improves the correlation across the EUV, the spectral range, to the level of these other indices, which are all better than the raw measured F10.7 across almost all the range. So then the next step is, what happens if we were to drive a model of the ionosphere, thermosphere system using this bremsstrahlung component of F10.7? And so this is work that was headed up by Larissa Goncharenko and Cole Tamburi, and Kent was also involved, as well as others on this call, I am sure. And the goal of this work was to develop a TEC, total electron content, so basically electron column in the Earth's ionosphere, at a single point in space over 19 years as a function of time throughout the day. And this model was developed independently using a number of different solar inputs. So that includes the F10.7 index, the corrected F10.7, this is the bremsstrahlung component, but also direct EUV observations, so from SOHO, the S10.7 index that Kent was just talking about, and the flare irradiance spectral model, FISM, developed by Phil Chamberlain. And so each of these, there were these 11 different models generated with different solar indices, and then the performance of these models is compared versus the data to figure out which solar input was most effective in this model. And so here I'm showing a number of measures of the performance of these models as a function of time throughout the day. And so the F10.7 is black. You can't even see it. It's hidden in this grouping of all of the models where many of them are performing quite similarly. The corrected F10.7, this bremsstrahlung component, is the cyan, and it has the largest errors and the lowest correlation coefficient, which is kind of awkward. So why might it be performing worse? It's not hugely worse than the other measures. I should say this gold line here was SOHO. These data were not corrected for the degradation in the SOHO channel, and so I'm pretty sure that's what caused these worse the models to agree worse. So why would F10 this correction to F10.7 cause the models to falter? Well, there's a number of reasons that I can think of. So first off, the TEC response to solar input is quite complex. So I'm gonna illustrate that here with a figure from the paper. So this is looking at the FISM2 models, which are the models driven with FISM2, which were found to be the most effective. And this is showing different components of FISM2 that were used to drive the model. So in addition to the FISM EUV data generated for the day of interest, they also used 24-hour, 8-day, 24-day, and 36-day delays in these signals, and these same delays were used for all of the different models. And for this FISM model, which was the most accurate, you'll notice that during the daylight hours between 6 and 18 local time, the solar input that was most important for this model was the sun from yesterday. So to predict the TEC right now, the most important component of this model was what the sun was doing yesterday, not what the sun is doing right now. And so this just illustrates that having the proper UV input right now is important, but the atmospheric response to these different solar inputs is filtered through a complex system. And so getting the EUV right now might actually not be the most important thing for some of these models.
Sam, you got about 3 minutes.
Perfect, thank you. I should also say that including these delay times sort of naturally filters out gyroresonance. So this is for FISM2, but of course the F10.7 input includes gyroresonance emission, and F10.7 is commonly used with a averaging technique to basically try to beat down the effect of these larger amplitude variations due to gyroresonance, and this delay sort of does that naturally. So some of that is getting filtered out in just the way these models are generated. Okay, other issues. The bremsstrahlung fit is of course a fit and not a daily measurement of the bremsstrahlung component, because we're only able to do that analysis during the MEGS-A observation period. So there's scatter around that fit, which could be causing problems. Also, the fit was derived using only cycle 24 data, and these models were trained and tested including cycle 23, which of course has much higher amplitude peak activity. So it's likely that the bremsstrahlung fit is not characterizing the highest activity levels particularly well. And the last thing, of course, is that gyroresonance is produced in large active regions, and therefore, including it in a model like this might actually have value, even though it's not directly related to EUV input. So for example, large active regions are going to be more likely to produce large flares, which are going to have impacts on the TEC, even though they may not be captured during an instantaneous measurement of F10.7 or even EUV. So having that information about active region scale encoded in the signal may actually have value in determining the the atmospheric response. So conclusions, I just want to start by thanking the EVE and SDO teams. This work was made possible by having the many-year, well-calibrated, high-resolution spectra from EVE, and it was not possible before then. I want to point out that F10.7 still has value even with modern EUV observations. It's sort of the backbone to a lot of the calibration that goes on, and actually the FISM2 model, which was found to provide the best TEC model, is sometimes driven by F10.7, so it's still a valuable measurement. We determined that the non-linearity between F10.7 and EUV at high activity levels is due to gyroresonance emission, and we can fit the bremsstrahlung component, which improves the correlation with EUV, but does not improve the TEC model. And And just I'll finally say we can actually make this determination between bremsstrahlung and gyroresonance using spatially and spectrally resolved F10.7 measurements that come out of, say, the EOV, so the Owens Valley Solar Array. So that's all I wanted to say, and thanks so much.
All right, thank you, Sam. Unfortunately, there's a whole set of conversations going on in the chat, and it's hard to pull specific questions out. I'm going to ask one real quick one. Typically, with the Thermosphere Ionosphere modelers, use a combination of the F10 and an 81-day averaged F10 in pretty much equal parts. Does that help with? Is that similar to your bremsstrahlung component, or is it? I mean, it's a crude estimate of that, but
yes. Basically. Actually, I'm going to go back. So yes, that's in my backup slides is that it is typically averaged over 81 days. And I'm actually going to go back to earlier. You can see very earlier here, the variability in F10.7 over a single solar rotation, it can be much larger than what's observed in the extreme ultraviolet. And so this 81-day averaging was sort of a crude method of, as exactly as you said, just beating down these individual rotations that were anomalously high. But and through this analysis, we are sort of able to say definitively that this is due to gyroresonance emission from an active region. So yeah.
All right. Good. So moving on, even though we're a little behind, let me know when you're ready, Frank.